up and I will run and be back. All right. All right, I will leave you two while I go get the pointer for him. So it'd take me about 7 minutes to walk there and back. All right. This
You want me to
mic,
get going?
hold on a second. This mic picks up really, really well. So yeah, you'll be able to do that. And Tommy, you can start anytime.
So, Alireza, give me a thumbs up in the camera if you can hear me well. You hear me okay?
Yeah, I can hear you.
Can those in the room hear me okay? I'll talk loud.
A little bit louder.
Maybe
Hello.
Maybe a little bit louder.
A little bit louder now. Hello. Can you hear me now? Let's see if I can adjust my device settings and turn up my microphone a little bit. Off noise suppression. Okay. Hello. Is that a little better?
Slightly louder, please.
I'm as close as I can get now. Hello.
Here. Yeah. Okay.
So good morning, everybody. I'm pleased to introduce Dr. Tofangchi. He's received a BS degree in mechanical engineering from Sereis University and a Master of Science degree in applied mechanics from Sharif University of Technology, Tehran. He earned a PhD in mechanical engineering from the University of Illinois at Urbana-Champaign in 2015. And he was under the supervision of Professor Saif with a focus on understanding the mechanics of axonal contraction. And that's part of his talk today. He was a postdoctoral research fellow where he focused on designing various types of force and stiffness measuring sensors with several orders of magnitude and measurement range. It's exciting stuff he's going to show off today. He was with Dr. King Su, who has left the university, but he was in the advanced manufacturing lab as a senior research associate, where he was focused on process development of hybrid ultrasound fuse fabrication techniques to fabricate PVDF-based smart soft sensors, which you'll see today. And he's now in Dr. Popa's group, and I guess my group and Larry since 2018, where he's contributing to a number of projects. It's really exciting work that he's going to show off today. He's a recipient of the prestigious Othmer Fellowship Award, has 3 patents and several peer-reviewed journal articles. So welcome, Dr. Tofangchi. Looking forward to your presentation. It's all you.
Thank you, Dr. Russell, for kind introduction. And thank you also for the department to having me here. It's very exciting and inspiring to see new faces here. First of all, am I audible? Okay, let's get started. As you see, this title's a little bit mixed up of my previous work, as well as the current research work I'm trying to run off, but that's sorry if it's a little bit looks spattered. So starting with the first part, mostly. The second part must be the renewable design specifically actually the different storage in continuation of the industry. So that is the price for the CPP of the system inside. And then followed up with the design of the channel management CPP technology to self-control with the then that we demonstrate the several applications, the internet and the working verification. That's the purposes. Yeah, starting with the this image. So as you know, neurons actually are the connecting blocks between the neural nuclei with the seed. So essentially, the neurons send signal like the cerebral nuclei to the seed, but sometimes they don't pass. If you look at path, it's then from the premium microphone and the ether. So the packing is kind of similar. It's transferring electrical signal from the cerebral junction. And then in detail, if you look into the synapse junction, what happens, what comes into the unit in terms of the neural language is the basically new transmitter process. So the new transmitter of the sphere like a sphere, usually a lot of the synapse junction will be reached, and then they will move on to the next step. Either another synapse or another. This is essentially how the moving communication. So the higher transmitter activity units, their effectiveness what the new transmitter transfer. There's no other way that the so now let's see a lot of countries. So we know the brain rock indices of the country. That's the first country. You look at the fourth, what's the country that you say? So this is one keep in mind. And then let's look at this interesting study this is the previous board that motivates now. So this study is really remarkable, but very simple. What they did, they took the American let's say a normal condition, like and then they taught the action with the radio. And they observed that the new transmitter going to be done. The test, right? This should be a key affair. Which is what happened. But that the market happened. And the answer to the lost statement the answer the market happened. What they are really is that these contributions to feel that happening. Almost education. So this strongly suggests the connection of the kind of thinking with density, right? The methods required to prove the mechanical functions of implicate the activation of the real constitution right? So, and then following that, there are a few questions pop up here that, okay, is there any tension exists in the action? If so, finally, the service. So you have the scientists how we get. Because it's not what's going on to do. Now, you're running the things that why do you not want to why question that's a Nobel Prize question sometimes. So focusing on these three questions, I start with slide and another system. That's a slide that's around like pick them with right when he was live for 3 hours. When I dissected Like I said, you get a single axon and the size of about 100 micron. And then, so what we did, we exposed the single axon and use a microforce sensor to see what happens here. I'll talk about it later. So it's about 1 millimeter by 1 meter force sensor that can engage with the axon and pull. Once it pulls, it can also use the force that exerted through the force sensor, and therefore we can find the return outputs in axon. And this is how basically works. So we look at how the force evolved in the force sensor, and we plot it. And see, we'll get back to that image next. Here you see the force sensor engaged with the axon, and we actually pull it. Up to this point, you see a like linear response, right? Like a spring. So the axon is basically highly elastic. But what happens, what happens if you have a spring underneath the force? What is the force in the spring? But this is not the case here. When we release the axon, actually we always have a non-zero intercept. It says that it is from the axon. So we tried many axons to get it through. So that suggests before we close it, the axon this is what often saw in the couple of behavior, right? Because it's down here on the prison. So it suggests that there is always a non-zero intercept distance from here, that varies from here into another angle. So when we extrapolate, we can kind of estimate that. And then we continue. When we basically hold the action, we start to relaxing. And when we let it go, like before we slide or wiggle shape, and build up the force to the same level as it goes in the so this cycle we can do many times. I've done it over time. So what does it tell us is basically force regulating to tell us when you feel the action or drop. However, when we want to be compulsive, the action build up the people. The always says this against you, right? So I think the action force being again. That's why we call it a regulation mechanism. So when you feel it, it's not, it actually doesn't like it, but when you let it go, it's good. After zero, that's also not good. So we try to build up something. But this is what he's doing, okay? This is the what let's do. So in image, when we push the axon from one side, you see once you push it, the tension immediately goes to zero, right? You have to pull. But the internal machine will start to work in the tension. basically shorten the lens. If there is a needle, of course, action cannot be hard. The only option he has is shorten it, right? So this is second time and a third time, and can continue many times like this. So that's the image of that. So when you put the action on one side, over a few minutes it's shortened. And then again I put it continue to shorten it. It can shorten its length by 40%. You can actually raise the speed of going. How is it possible, right? But to make it floor, you raise the both ends with the force. So you try to build up the tension. So this is what's going on, right? This is coming what I said. We pull the action, so we're starting from the rest tension here. We pull it, we show the linear elastic response, but being pulled, it also starts to relax and drops. And then when you let it go and you load it, drop to zero, right? But it actually will build up the tension nearly 20 hours before. So this cycle is the life cycle of the needle. So you can compare it to the needle and actively restore what it breaks. Anytime. There is a drop. And then the other side, when you compress it, like here, is the negative extreme. When you compress it, initially it's shortened, but you feel that it's tension. You need the same amount as before. And when you continue to compress, like here, you need that too. It's really working strong in a way that it can only force range within a certain amount. It's still this question, why question you here? You haven't answered yet how. Okay? You describe what question. So we continue to see how this happens, but does it help us to understand why? Let's see. Okay. So. Here, trying to answer the question. Try to say how this contraction happens. But again, unfortunately, it doesn't have a knowledge. So it's just really nice combination of you can answer me what how. So here we try to convert in the way you understand structure of our machine is not good. There's nothing else to understand working like the mining like you know the cell is the cell that wants to go. We need to do nuclear and also the molecular machine that might be right? So engineers not from one by one. So in the normal case, when you compress the neurons, all this contracted thing is I've done it 2 years. Couldn't stop it. Because all the other scientists believe that there is no activity in the work that they are doing. So you couldn't try these drugs that basically not down. But anyway, I've tried. First, I tried to ATP in vitro. ATP is the metabolism. You know, even if the integrate, it is stopped. The contracting steps. It's first, second, but the short of this contracting is not here. Some people say, hey, this is just funny. Even when you apply the drug, this drug basically inhibits the energy because it actually stops it. These two, basically, one of them inhibits the mind. Mind like you. I feel too like basically really nothing. It's not nothing. When I inhibit that also stuff. And also when I stop the acting, that is nothing happens. But not for multitude. When I stop not to go with contraction, even increase. So we end up with this model, right? So we can read what is happening. So basically, here, what we can do construction. So the acting and the minding are involved, right? The rock and the know, so when you put the acting, those acting and the minding are involved, right? So once the tension drops to zero, they get loose and the rock to be constructed. But when they're tight, they're not constructed. But once they compress on one side, like this atomizer the fluid starts to confront. It's not something. This is not there. So we want that what to observe what's happening, and we try to also explain how this happens. Stop simulating. So it took 5 years to break this problem. With the following week to kind of know that completely maximum is clean up to the way but it's still not close and whole. Why is the real so again, it's still the only rock and that it's really even line. This is really a correct for people that the opportunity is the same. There are some hypotheses. And I feel hypotheses. If you know, why do you even describe the future? Why do all these fit? Even if you calculate the unit, you see the future. So one hypothesis is the real difficulty between the well governed, it's not the electric, right? It's probably around it. Planning of sound and thought. You report the control, sound control. The other function is the function, the skill of students. The high frequency of skill of sound. What is the doctor give what happens? Skill of sound happens. If you sound enough travel around the you have things happen. When you see that happens to people that travel beyond their that might be a reason and reason. Another reason could be is the transport of the biomolecule around the you don't actually be up to the because all biomolecular supply around the you can actually translate it individual, everything else covered. So actually 50 to coverage to get the molecular machine travel from the weak line to the long cancer. That could be another reason. The fourth reason could be very important. Some other thing that has statement we have to so some of them must be already to open. That could be one reason. But again, there's no certain answer why the axon always pull. And at the end, I close with that for this section. That is the fourth center that we use. The work and the mathematical modeling is down. It's the ninth center. So we could take care of that. Time or not feature, if you really have to decision to look to the message. The new tool is not damaged, right? So this is basically stealing versus the the other feature of this center is you can operate and so you should operate properly without but it exhibits a long range of the measurement and always mean and never exceed the uniform of the silicon. So it's definitely work for our case. So let's move on the second part. Yeah, focus on the neurons on people. So this is the imaging of the so people basically so the whole there's one connection between the for example, for interest, but here again, how to get to the site to use the local love. That's even quicker than it takes time. The left side done the also the other thing also related to come up with some idea of how to design that to meet all these requirements. So basically, the idea started with happening at the time. We have a fiber in compression. We can do the down second unit. When also first inside the fiber what about me? Another thing, if you have that force and indent that, let's say, fiber into the tissue, you certainly not to be efficient. So the best thing is when you can certainly tissue, that's tissue. It's not hard, you need to the tissue. Allow the tissue for company structure. Even if you increase the natural force, so we can have a micrometer here and start to putting the rod to these structure and watch when it comes. So we can read out the mountain of the needle, and you also can measure the cable. And in conjointly, you can find a changing length of the rod. Because of what the sequence is not completely then from that equation, you can calculate that the thickness of the tube. So that's the idea. But how to implement it, this is the device that we come up, basically start from scratch. We don't put any of it. So that's the fiber actually here. That go all the way from the tissue to the ground. The magic part is the tissue. The tissue allows the effective use of the fiber and grade. And for long fiber, you would count as the fiber. When you see the second length, for a particular tissue, you have to use totally unequal to itself. just some intricate mechanical here, how it works. There's the fixed bar here and then multiple interlock it allows me to have a very good lens. So when you touch the tissue here, the mechanical trigger, and you read out the angle here and the mount of the mercury to the top, and the difference between the picture. And then from the first one, you can estimate the picture together. Right away, to the camera, read out the angle, to read out the signature of lens, and then maybe we have to fix the stiffness. So this equation also tells us when the sensitivity of monitors is highly sensitive to the diameter and the lens. We vary the diameter and the length of the project. We can see the large range of sensitivity to get the order here. So that's why this device gives us a large range of so 1.1 kilopascal but 1,000, 3 order of magnitude. That we have shown is possible to do that. So here's more details of how we calibrate things. We need a solid surface and scale to calibrate it, make sure the reading is correct, and also we need an optical camera and calibrate for the angle reading. And the rest would be reading. So we did the maybe not much time. But working on optimizing the timeline, get very good and additional range of the sequence reading. So we have done with many PA gels. So let other people graded stiffness field as we know the stiffness in that time. That's one way. Another way is using only and when we compare with what we did from the Beacon, you can remember that the elastic so you see it's pretty much the lowest thing there actual range is the so once we have that validation, we moved on and did some actual tests. Like this week, and they said, okay, spend something on testing the most that's a time yes, and test the device, but the part of the country. And got data and got this result. Here you can see the motion, right? Yeah. So when it basically then we stop, but we need to get preoccupied with the what that the value, the rest, the active. So then the clock is independent. And you see the green one is noticeably above the average. And the purple one is slightly lower than it. And then they affirm that the green one is the green. I mean, the green one is that the difference. What you need is about, 0.5 to that not quite. It's you have to get the way to see it. When you use a word, so you have to. But the way you express is a certain, we use a different word to see the different, it's not true. These are just expensive but training. Great. This is my masterpiece for outcome. That's why we very accept because that's my taking of stories. Because maybe you from walking down, really expand them. So, we published in scientific report. My name switched because I left the lab, so I do all, I start from scratch, do all the questions. Definitely using coding to polish the device to make sure that reading is correct. And like what happens pending, this is almost the last part. The last part is designing from techniques where so the idea is using some of so these polymers are usually what there are really the functionality, right? How do you really the line? When you feel them, there's one of the skills not around. Once you get the line, if you are highly voltage or polling, once you conform, the point starts to stay special. I don't go that detail, but what happens when we change the layer of this poly with the and the cosmic director, the copper and aluminum belong that or perpendicular to the poly. What happens when you deploy the compressor? Initially, there are some equipment as electrostatic charge in this wire. When you deploy it, it needs to there are some disturbance, charge, stuff, all the electrical currents to indicate and connect that particle with the reading of light experiment. So therefore, this can be used as a screen. So, but the beauty of this work is you can really treat it. The physical being is almost not influenced by what's going to be down to the you can basically create one structure, three structure, and use it. So here we see a different things where there are many molecules that we can't create. The equivalent of the polymer, the two sides of the molecule, and each side you see very small, with light or very close to the other side. So and also parameters of the wave. Each of these can define the effectiveness of the device. So we are starting with depositing the free of the polymer, and then after that, we use the ultrasound for security to inject the wire into the polymer. So we create the such devices, right? We basically want to control the structure of the polymer and the liquid. So what we did here is and not just see in performance, if we get started with something that also functionally functions, activity between slowly the work on something but we can function. We can start the but one thing to happen is certainly concentrate on the output signal. Let's say I was speaking to a monkey. I was wondering if it's kind of these sensors are dynamics. Before we faster, we take policy. So this is manifested here, right? So in 1 second frequency, when we perform it, of course, when the performation is for 3.5 frequency. But on the other side, because the given strain, when you increase the frequency, goes with alternating. So you have a given regional conflict of your ability to but frequency is a large frequency, right? The signal output is continuous early and frequency, not a frequency. When you start region, the alternating is not constant. They only work frequency. So we did some also design some two-page to this because you need to know a certain frequency at the particular frequency. This is the also one that if you allow people to think that very dramatically you cannot be able to come in the amplitude. The frequency of the is very big. And then this is how we characterize the sensor if you want. The sensor between the different here, the Mechano and the output signal. Here, there are some applications you can see. Hopefully it's not boring anymore. So one of those is 1D sensor attached on the TV like the glove. Carry the unit is not ready to move, but when the finger moves, you see the signals on the screen. The quality is not that copy laptop plus the regular file. But it works well. The other one, that sensor I have in the finger, you know when the finger started vibrating, the amplitude was up, right? Time up. So that exponential decay, you can see it played again. You see this timber amplitude goes up, mechanical dissipation, right? And that's exactly depicted on the screen. So that electric signal output. The frequency of the vibration is exactly nicely for the mechanical frequency. And this sensor is great for frequency capture also. So I use that as a strain gauge there. So you can, they told me that we can a direction. This sensor detects the strain of any direction. It can reflection, transcendent, spectrum, unlike the conducting sensor. And I guess finally, this is another sensor we fabricated here, the 2D sensor, and then so the capstone team managed to make this wireless, so we made the format to the corresponding signal from these two on the display. That's a nice fabric. And finally, we have some application in the reference. You want to look at reference pioneer is from the developer from this. Here is designed to get started like the way you just talking to the first. So you focus on all of the people and stuff. And the monitor because you want to really do it, right? You like to quantify. You want to visualize your effect, right? If you know, if you can see the monitor in front of them and then you move, like the area you can slide it and visualize it. But in addition, you also need to quantify. It's quantification here, right? Because you need to control, like, let's say, 1 week, so we are talking figures of the plastic, right? You need to control of the last week. amplifier, not all of the signal. And then we show the output too. Again, like that signal, sometimes it's enough. And then we restore it in God. If you have to believe the state, the fact that it's working is now, how similar is it? But we develop it. And then you also need to study for quantitative based on the also based on the density. The density is like the scale of definitely like this one and the peak also, and also the number of peaks. But this central still working then, when silicon phonics pick up this variation. Again, this work previously have started with the anatomy of the PhD student of Dr. Russell, but this is a different approach with a different sensor. So quickly, we started with the design some mechanical enclosure. So the purpose of this design is to prepare all the skills at one time. So here is the thing. We want to support this feature, we need to put take this feature and the bond. A lot of units, you know, so and the floor, this thing, a lot of units, you can't see one assets in so here is design interface, basically, that when the response to the tank, when let's say this figure in the arm, when you compress it, if you want to receive a push. But the sensor is being deployed only at one point. You usually see the deformation at one point. Let's say we have a one force here, the same force, but it acted at different time. It could be the same, right? The same deformation. But in mechanics, when you have an arm, moment, right? But this is a specific design, like we have a load at different locations. Let's say something different, which is something like a main design. So this is a special inflation design, come off the ground, you test it, and basically you trigger all the force along the very upside and the electric outburst at the same time. So we attach them at different points on the field, and we did some testing. Here, so the result of the work is here. When the force action is independent of the position, what that means. So when you apply force to take a deflection, you have to get the same slope everywhere. Basically, the stiffness of the enclosure is uniform everywhere. It's not have energy. And if you have a distributed force like in RDS, integrate all forces directly at the same time. So hopefully I can run it. Basically, the force applying from the top at the center point becomes the sensor only at one point. That's the purpose of the mechanical design of the enclosure. So we embedded a different spot of the chair, and we'll see the result of it. These four the electrical thing, they basically manage to collect the whole signal and wirelessly transfer it to the physical display here. And what we see here, there are three You can install in the chair, and I think I sit on it and rock it, and you see the result. So you can observe the signal output simultaneously from the install. So each of this signal basically can interpret it. When you calibrate it, you can interpret what that signal can be. From different spots, different signal, and you can integrate and work over time and compare the healing progress and just looking at the signal going a lot of data. That I think Jonathan can help us to interpret their signal. So that's the, I guess, we are in one part left. This is another example. We use those in the sole in the shoe. So this is in the gym. That's from Dr. Young too. So you clearly see distinct regions when we use this sensor in the shoe. During walking and running, we also have it running. So we can identify distinct regions. This region can be calculated with technique. So when you run a lecture, start to the time left is one is the target is one. Time working the ground. That is one in this. You can really calculate it using this compass map. I think with that, I conclude. I skip the summary because then I'll get with some question and learn something more about knowledge. So thanks to the team, everyone, and also thanks Betty. Sorry, and that's the Emmy and electrical capstone team, great team, and everyone here as we work. This is obviously not only my work; it's always teamwork. Especially thank you, thank Dr. Larry, Dr. Popa, Larry Director, and Dr. Russell, the PI of the Lucky Field, and the laboratory and the students and all various staff and students. I just want to take advantage at this point to you know. In terms of the numbers, that's we have 50 million metric tons that so particularly if I want to say something about the work that we receive for the packaging, the special experiment so for finding particularly like this, we have 1.3 million micro, and especially we're looking for conditional signal that was
I was wondering if inserting into if you select pages, you can tell what pictures around it. And I know that access to countries to use it and read out the syringe. Insert the another person
Thank you very much. I apologize for waiting for you to stay here full time. But everybody please, sign in and just before you go. Just choose pizza that there's 10 cups and regular cups when you talk about. Thank you. Thank you.
Thank you.
Let's see if, Dr. Rousseau.
Here.
Yes.
Still here.
All right, hold on, I'm stopping there we are. Stop sharing. All right.
You sent some virtual pizza?
Yeah, I went and got a Papa John's. So let me stop this recording too.
Thanks for your presentation, Dr. Tofangchi.
No problem. I hope